Okay, so here are three reaction problems so carbonyl chemistry, aldehydes, ketones, carboxylic acid derivatives, some oxidation. In David Klein's book, which we're using here at Wake Forest, you'll find this chemistry in chapter 12, 19, and 20. And maybe 22, I can't remember for this one. So anyway, you've got these on the board, hit pause, work the problems, and then come back and get your answer. Okay, I don't have to pause. I always tell you guys to pause, and then I go to try to pause I want to pause. So let's start at the top. Okay, so I don't have to cover that up yet. So we've got an alkyl halide, and I gave you all these chapter numbers, and honestly the first one is probably the simplest reaction. Set this down. So this top reaction is a Wittig. Okay, so this one is an example of a Wittig reaction, where we're going to make the Wittig in the first place. So we're going to start with triphenylphosphine and an alkyl halide. This is just going to begin with an SN2 reaction, and we're going to get, so the product of this first step will be this phosphonium salt. Let me make sure that's still on the screen. I can't. Barely. Watch out for, there we go. Okay, so first step is just an SN2 reaction. This is real fun to do and I like reactions that give you a precipitate, and depending on the solvent you choose for this, often you just get this white crystalline solid that falls out of solution, which is the phosphonium salt. Okay, the second step then, and remember also the way we use these numbers in a reaction scheme. This says so we're not mixing all of this stuff together. First, we treat this bromide with triphenylphosphine, so you would dissolve one of the two in some solvent. You'd add the second reagent. You never want to put the reagents together without solvent, because then they're concentrated, react too fast. So dissolve this with the bromide, add triphenylphosphine to it, or vice versa. Second, we're going to isolate that salt. So we're going to precipitate it, or rotavap off the solvent. Probably not going to purify it, but then we're going to treat the phosphonium salt with N-butyllithium. And so remember that N-butyllithium is just a really strong base. So this is going to react as if it's that anion. And again, the carbon-lithium bond is pretty much completely covalent, but the molecule reacts as if it's that anion. And so what's going to happen there is that really strong base is going to take a proton from the carbon bonded to the phosphorus, and we're going to end up with this ylide. Right? There's a resonance structure there that has the double bond between the carbon and the phosphorus. So you get this ylide. So that's step 2. Okay, and then finally in step 3 we treat with the carbonyl compound. Now I've drawn this carbonyl compound to have 2 different carbonyl functional groups. So we've got a ketone, methyl ketone down on the end, and we've got an ethyl ester here on the other end. So if you've read chapter, which one is it? 19? I think it's 19. Ylides in the Wittig reaction don't react with esters. So it's only going to react with that carbonyl, the ketone. And so the product we're going to get out of this, I'll stand in front, we're going to get the ethyl ester will remain intact. Count your carbons. There's 1, 2, 3 carbons between the 2 carbonyls. So 1, 2, 3. All right, now that carbon, let me put a little red dot by that carbon. Okay, so that carbon was a carbonyl carbon before. So the Wittig reaction is just going to break the 2 bonds of the carbon-oxygen double bond. So kind of like the ozonolysis reaction. And it's going to replace them. It's going to also break the two bonds between the carbon and the phosphorus. For the mechanism, either go to the book or go to our class notes, or maybe I'll do a mechanism one again. But remembering how to get the product, we're just going to take the negative carbon of the ylide and double bond, make a double bond to the carbonyl carbon. We're going to get rid of the oxygen entirely, which is going to bond to the phosphorus. So now we have to count our carbons. There's 1, 2, 3, 4, and a methyl group, 5 totals. We're going to get a double bond here, right? In place of the oxygen, that's that carbon. Put a blue dot next to that. So I don't usually do this when I draw these on the board anymore. I've been doing this a while. But I really encourage you guys, any of you who are beginning organic students, and probably if you're watching this video, you're a beginning organic student. Otherwise, get a life. Anyway, you probably should do stuff with this. Label, count the carbons carefully, because those are easy mistakes to make. And they jump out at your grader's eye. So, blue carbon is bonded to a CH2 and then an isopropyl group. I'm going to draw it this way. And again, count the total carbons you've added. So starting at the blue, we need to add 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. That looks right. And then we also get a stereoisomer. Right, so, look, talking about easy mistakes to make. Double check everything at the end. I lopped off a methyl group. If you've been sitting at home saying, okay, Jones, put that methyl group in. The red carbon has a methyl group that stays in there, both of those. Okay, so now there's the product, right? Always double check your work. And again, you get 2 stereoisomers here, 2 diastereomers. You get cis trans, so this one's going to be, this will be a Z. So H is the low priority, methyl's low priority there, so high priority, high priority. This one is the Z double bond. That one is the E double bond. Again, stereochemistry is Orgo 1, but you should go back and take a look at it. We do expect you to know Orgo 1. So you get easy isomers. The book points out that in a lot of cases, the Z isomer or the cis isomer winds up being the major product in the Wittig. As I said in class, the actual easy ratio of a Wittig reaction depends on the substrates, it depends on the base and the counterion. So we've got lithium, we're going to end up with lithium bromide in there. You'd expect the easy ratio to be different if it was lithium chloride or lithium iodide or sodium bromide or magnesium bromide. Okay, so I haven't put anything about solvents here. The solvent is also going to affect the easy ratio. The point is about the Wittig, you're going to get a mixture of diastereomers. And as long as you tell me that, I'm good. Honestly, if you just draw one of them, I'm probably fine in Orgo 2. If you're a grad student, I would like more information. Okay, so that takes care of the Wittig reaction on top. Let's come down and do the green reaction here in the middle, on the middle board. Again, we've got an alkene, we've got an isopropyl ester, so that's going to be a common way to talk about these. It's an ester, a carbonyl bonded to an oxygen bonded to some organic fragment. So this comes from isopropanol, and then what is this? 1, 2, 3, 4, 5, 6, 5 hexanoic acid. So this is going to be isopropyl 5-hexanoate. Anyway, most people are just going to call it an isopropyl ester. First reaction is lithium aluminum hydride. Lithium aluminum hydride is a powerful reducing agent. Again, keep in mind that this is sort of going to react like H-, as you're just trying to keep track of what does the reaction do. This is not a mechanism. There's no actual naked hydride in there. But it reacts like H-. H- adds in. And then I'm just illustrating the double addition we get. This oxygen is actually going to be coordinated to that aluminum or bonded to the aluminum, but it can kick out isopropanol, isopropoxide, and we get an aldehyde. Nothing's happening with the alkene, okay? A carbon-carbon, most alkenes, we'll see a few in chapter 21 where this is not true, but most alkenes are not electrophilic enough to react with strong bases like Grignards or hydrides or anything like this. All right, so look at that aldehyde. Maybe that's your product. But no, lithium aluminum hydrides are really powerful reductant. If we've got H minuses floating around, and I can't emphasize enough, we don't have H minuses floating around, but lithium aluminum hydride would reduce an aldehyde. And so bang, bang. So we get two H's there, O minus, and then step 2, the water is just to protonate this thing. This is step 1. And again, let me draw this out how this would actually look. This is going to be bonded to some sort of aluminum, and there's going to be other stuff here. So these could be hydrides, they could be ORs, they could be whatever. When we hydrolyze this, we'll take off the aluminum part. And get that. And again, come back. When you work these problems, I'm just kind of, I missed a methyl up here, I'm kind of flying through there. Get the chemistry that happens. The chemistry is what happens to this functional group. What does hydride do to the functional group? At that point, come back and make sure you've got the other details, right? So I came through this up here on the Wittig reaction, and I'm like, okay, we've got to make a double bond between the red and the blue carbons. Make that double bond, and then double check it. Oh crap, I left out a methyl. So the same thing down here, count your carbons. Starting down at the alkene, let's put some numbers on these. So carbonyls 1, 2, 3, 4, 5, 6. So the carbonyl carbon is going to be that one. 1, 2, 3, 4, 5, 6. So I got the right number of carbons. Hallelujah. Okay, so carbon 1 is carbon 1. Lithium aluminum hydride and then some sort of proton source is going to reduce an ester carbonyl to a primary alcohol. So you go from a carboxylic acid derivative to a primary alcohol. Recall when we did oxidation, chapter 12, chapter 19. If you oxidize a primary alcohol under aqueous conditions, if there's water around, you end up with a carboxylic acid. So if you reduce any of these carboxylic acid derivatives with lithium aluminum hydride, you're going to end up with a primary alcohol. Okay, so last step. I haven't done step 3. This is step 2. So step 3 is Des Martin. This could be PCC dry, Swern. Did we do any others? Seems like we did some others. Anyway. This is an oxidation that just takes you up one step. So it'll oxidize a secondary alcohol to a ketone and a primary alcohol to an aldehyde. So we have a primary alcohol. There's no way to make a hydrate because it's under dry conditions. And so the final product is going to be this aldehyde. And again, count your carbons. Make sure you get the right number of carbons. 1, 2, 3, 4, 5, 6. Did. So this is 5-hexenal would be the name of this compound. And you might think, but we made the aldehyde. I made the aldehyde right over here. So why isn't that the product? And again, that isn't the product because lithium aluminum hydride reduces aldehydes. And so you just do the first reaction. Don't try to predict the product way in advance. Work through each step as it would happen, and we're going to end up with this aldehyde. So this sequence, lithium aluminum hydride and a proton source takes you down to the alcohol. Some sort of dry oxidizing agent takes you up to the aldehyde. And you might say, can't we just go directly to there? And there are some reagents, dipol is one, but typically it's really hard. Aldehydes are much easier to reduce than esters. Okay, so if we come back over and look at this step, this one, right, this step is slow. This step is fast, relative to one another. Okay, so aluminum hydride reducing an aldehyde, very fast. Aluminum hydride reducing an ester, relatively slow. Okay, so it's very hard to design a reagent that will stop at the aldehyde. Anything that can reduce an ester is probably going to be able to reduce an aldehyde. Like I said, we're creative folks and we've come up with a few of these, but a lot of chemists, myself included, if you needed to do this, right? If I've got isopropyl 5-hexenoate and I need 5-hexenal, I can fiddle around with a difficult reagent to stop at the aldehyde, or I can just like blow the ester away, go to the alcohol, and then oxidize it up easily. It's almost always a faster, higher yielding, less stressful way to do this transformation. Okay, one more reaction. I'm going to slide up now. If you need more information here, pause and write it down. I should have said, if you haven't done this reaction yet, pause, or if you think you've learned something, then pause and go and try it again. Okay, so here, look at the functional groups. We've got an alcohol, we've got a chiral center here, and we've got a ketone, a methyl ketone. We've got a nucleophile in ammonia hydroxylamine, and we're at pH 4.8 buffer. This means the solvent, so buffer is going to tell us that the solvent is at least partly or mostly water. My red pen's about to die. Yeah, you can see it. High production values here. Okay, so the solvent is going to, so this is aqueous. A lot of questions to ask. Can anything happen to the alcohol here? OH is not a good leaving group, so you can't do SN2 chemistry or anything. If you want to get rid of the OH, you need a strong acid or a strong base. pH 4.8 buffer is relatively mild, like a soda. Chiral center, anything going to happen to the chiral center? Probably not. It's not next to a carbonyl, so you can't deprotonate that thing. There's no functional group on it. So probably nothing's going to happen to that chiral center. You've got a ketone. Ketones are electrophilic, so they'll react with strong nucleophiles. And honestly, at this point, I'm drawing this out. You guys should have looked at this one pretty quick. It said you've got a carbonyl, aldehyde or a ketone, and an amine nucleophile. And so this should react pretty fast. And so what's going to happen is under slightly basic conditions, amine nucleophiles. So this is true for basically anything like this. R in this case is OH. One other thing I wanted to point out, a lot of people see OHs and think, oh, that's an anion, it's hydroxide, right? That's the first way you guys see OH, is as a hydroxide. But this alcohol, that's an OH written there, that's a covalent bond. This is also a covalent bond. So the way this molecule looks, I do a full, I hardly ever draw full Lewis structures in this class. So there you go. All the electrons and everything. So that oxygen's nucleophilic, but so is the nitrogen. The nitrogen's a little more nucleophilic, and it can make two bonds. So the product of this, not a strong enough nucleophile or base to do anything with the alcohol. pH 4.8 buffer is not going to do anything with the alcohol. So that alcohol just sits there, watches from afar. We're not going to mess with the chiral center. So just keep all of that the same. There's your product. This is called an oxime. And if this was our NH2, it could be an amine, R could be an amino group, or the only thing R can't be here is a carbonyl. R is not equal to a carbonyl. Okay, that would make this nitrogen an amide and not very nucleophilic. But pretty much everything else, you're going to get that product. Okay, and the other thing here, you can also get cis-trans isomers around here. So up here on the Wittig, we got E and Z isomers. Here we're going to get the same thing, right? That carbon-nitrogen double bond can be, that OH could be pointed over this way. With nitrogen, we don't talk about this a lot in stereochemistry in Orgo 1, but that nitrogen can invert really easily, and so you have both of the stereoisomers here, and they go back and forth, even just in solution. It's because there's a lone pair is on the other, right? If you think about this, the other one here is a lone pair, and that can actually invert convert. There's a little bit of that orbital on the other side. And so it's a lot easier to invert a nitrogen at a stereocenter or in a stereoisomeric alkene. Anyway, there's your reactions. So top to bottom, the Wittig, reduction oxidation. This board does not want to stay down. I'm glad I picked it. And then making hydroxylamine, or sorry, making an oxime with hydroxylamine and an aldehyde or a ketone. And again, this reaction is not going to work with a carboxylic acid derivative. All right. Cheers.